In this video, we're going to deal with angular momentum. The symbol for angular momentum is L. It is a rotational analog of linear momentum. It plays a fundamental role in the information about how the universe is formed, why galaxies have the shape they are, why protons and neutrons can interact because of their intrinsic angular momentum. Angular momentum is one of the most important and fundamental concepts of all of physics. The definition of angular momentum says that if you have an object, say this little ball over here, and if you have some point in space upon which you wish to determine the angular momentum about an axis, say this point that's green, then there is a vector r from the axis of rotation to the object. If the object has linear momentum p, shown in the red arrow, then the angular momentum about this point, which I'll call O, can be computed as follows. The angular momentum, by definition, is the cross product of the position vector to that point crossed with the momentum vector. Now, we know what momentum is. It's mv. So this is r cross mv. And m being a constant, you can pull the n out front. So it's m times this weird cross product between the velocity and the position vector. Now, while this is the definition, it's not always what we use to calculate angular momentum, especially for an object that's composed of many particles, all having different velocities and hence different momentums. In order to do some computations, let's look at some things. First of all, angular momentum is a vector. It's not a scalar, and it must be added up vectorially. Its magnitude is very similar to the way we see with torque. It's equal to r, the length of the r vector, the length of the p vector, and the sine of the angle between those two. Now let me draw carefully what this means. This means that if you were to take this purple arrow and you were to move that purple arrow by sliding it without changing its direction, then it would be out here. So I just slid that purple arrow on out. This angle here is the angle theta. And what this formula says, this is the length there. In fact, I'll just put it in that color. That's the length. P, that's the length of the red arrow. And then you have the sine of theta. Now, usually in problems, this is not the most convenient form of the formula to solve. What's more convenient is that when you have an r and you have it connected to some p like this, and you think of that r as going on out like this, what you're looking for is how much of the p is perpendicular. Call it p perpendicular to r. So a more useful way is to usually say how much of p is perpendicular to r, or p times how much of r is perpendicular to the p vector. And then, just depending on whether you need a sine or cosine, it's whatever you need to find the perpendicular component. If you have this angle, then it is the sine. But if you had another angle, for instance this angle or something else, then it might be something different. It could be cosine. Now, for the direction is given by the right hand rule. And for us, because we're usually doing two-dimensional problems, what we'll do is we'll put our axis, and then we will put the direction that we are going to wrap our right hand fingers in, and our thumb is in the direction of a positive L. So if I wrap my fingers like that, my thumb points out of the page, and that's what I mean to be a positive L. If I had done it in the opposite direction with my arrow, then I would have meant a positive was into the page. So the angular momentums in our problems will either be pluses or they'll be minuses, but they won't be anything different than that. Now, a key point. A lot of times people think that you have to be rotating to have angular momentum, and it's true that wheels that rotate have angular momentum, but an object doesn't have to be rotating. An object can be going even in a straight line. For instance, if you had a proton here, or let's say the nucleus in atomic physics, and you had another particle, maybe this is a proton, and the proton was going like this with some velocity, then it correspondingly would have some p. Then it has some L, because it is not exactly on the same line, so it has a perpendicular, and it has a P, so it has an L. Notice how I chose to use this distance rather than what you might think I would use, which is the distance here. I'm not going to use that for R. I know that's the R. For an axis right here, but it is actually easier, since I know P is like this, to take this distance, the perpendicular distance, multiply it by P to find the L. So even though it's going a straight line, it can have an L. What it has to have is a P. It has to have a perpendicular part of R. If it has those two things, regardless of the shape of its path, it has angular momentum. Now, for a rigid body rotating about a fixed axis, the magnitude of the angular momentum can be found with a much more useful formula, and that's this formula. L is equal to I omega. This is from the big board. We've used the big board to replace P equal mv. So replaced linear momentum with angular momentum, replaced linear inertia with the moment of inertia, and we replaced linear velocity with angular velocity. And this is the one that you'll use in most of your problems. It does say about a fixed axis, and in another video I'll talk a little bit about some things we kind of swept under the rug with I. Now, what this thing is saying is that L is I omega. That's just the magnitude. It says that this direction of this L and this direction of this omega are the same. So if you have an object like this spinning like that, and you wrap your fingers, your thumb points straight up, and that's the direction of omega. This formula tells us that that's also the direction of L. They point in the same direction. For the object right next to it, it has the same omega, and it has the same L. Now you could also ask, what about torque and angular acceleration? Let's assume that this is speeding up, and this one slowing down. Well, if it's speeding up, then I also know that alpha is in that same direction as omega, and torque, some of the external torques, is always in the same direction that alpha is. Over here, since it's slowing down, alpha is pointing this way, and that also means the sum of the torques is pointing down. So torque and alpha are aligned, omega and L are aligned for an object that's rotating on a fixed shaft. Example of a problem in this sort of area. What is the magnitude of the angular momentum of a uniform disk, 5 kilograms, radius 0.2 meters, rotating at 0.4 rads per second? L is I omega. I, for a disk, is 1/2 mr squared. So I is 1/2 5 kilograms, 0.2 meters squared. I put all that together and I find that it's equal to 0.1 kilogram meter squared. L is then 0.1 kilogram meter squared times omega, and omega is 0.4 rad per sec. So put that all together and I get 0.04. And you can put kilogram meter squared per second, or you could, for instance, say joule seconds. You could also say 0.04 Newton meter seconds. You could also say 0.04 kilogram meter squared per second. All are good. They just emphasize different things. All right, in the next video we'll deal with Newton's second law.